मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
And by now we have understood that the crux of finite element analysis is interpolation. It is that concept that helps us to reduce an infinite degree of freedom system to a finite degree of freedom system and make us focus on the so called nodes. So, it is very important that we understand what is it there for us to look at on this interpolation, or what are the things that we should be focusing on in case of writing down this interpolation. I think we as a passing mention, I already did that when we put down the interpolation function, but let me just summarize it and put this whole concept of interpolation in proper perspective. This becomes especially important because if you remember that when we did that example, we had what we called as a jump or a discontinuity in the stress as we moved from one element to another element. Okay, this I am sure would have surprised you quite a bit because people do not understand this kind of stress jump, but it is very clear that the stress jump happened again because of certain things we did in the interpolation. So, it is not that the results are wrong, okay, but it is important that we understand what we are in for, right. So, hence it is important that we look at what are the requirements for an interpolation function. One of the things that I want you to realize right in the beginning is that many of the concepts we are talking about now is not only for structural analysis or displacement based finite element analysis. Many of them are applicable even if you look at other problems, say for example heat transfer. If you want to analyze heat transfer, again interpolation is a concept which we will be using, is that right. So, if you are looking at say electromagnetics, totally different area, then again this concept of interpolation and many of the other things that we are going to talk about in this class and in the next class are important. Hence, usually many people and textbooks do not just say u and v, but put down what is called as a field variable. Say many people use for example a field variable phi. Okay. What does it mean? It means that this variable phi can take on values like u, or can take on other variables like u, v, w, temperature T, whatever it is, velocities, we are going to see that later in the course, velocities, all those things are generically mentioned by means of a quantity called phi. So, many people express the concepts of finite element analysis through a field variable phi, which is a generic name for u, v and so on. Is that clear? So, whenever I use phi, then immediately you should understand that phi can be replaced by displacement in the x direction, y direction and so on, right. So, let us now look at what are the requirements of the interpolation function. In order to look at that interpolation function's requirement, we have to concentrate on what we called as the functional phi p. So, what we have to do first is to go and look at this expression for phi p and then look at the derivatives of the field quantities or variables that exist in phi p, right. There may not be any derivative, which rarely happens. There may be a derivative of the first order, there can be derivative of second order and so on. So, the first thing that we have to do is to go and look at the derivatives that exist in phi p. Let us say that the derivative exists till the order say m. Okay, this varies from one problem to the other. That is why I gave right in the beginning of the class, I said that we are going to talk about a generic procedure. So it's not, in other words, what I am going to tell you or what I intend to convey is that this phi p what we talked about is not only applicable, or the functional concept is not only applicable for this displacement problem, but is applicable to a range of other problems as well. As long as you are able to express this functional, whatever we are going to talk about are applicable. Okay. Hence tomorrow I am going to do, or later in the course I am going to do temperature, okay, or heat transfer analysis through finite element. I will not explain all the things what I am doing now. I will just pick up these concepts and apply. Okay. So let us say that phi p has derivatives up to an order m. Now what is m in our case? What we did, can you please check up that? What is this m in our case? Or in our case in sense that what we did in the last class, m is equal to, look at that, du by dx is what we had, 1, correct, okay, m is equal to 1. It may vary, we are going to see that later, that it may increase, m is equal to 2 and so on. Okay. Let's look at that as the problem comes. I will point out what that m is. I don't want to confuse you with more examples on this, just we will take whatever we have done so far. Now one of my first rules is that the interpolation function should be complete to this degree m. So should be complete to this degree m. What do I mean by completeness? You remember I had said that it should lower or correct. So the lower order polynomials should be present, that is very important. So the first thing is that it should be complete up to the degree m. Right. The next thing that we are going to talk about, why is that we said this more physically? There are other mathematical reasons, but why is that we said that it should be complete up to m? Because if I start with say x cubed, okay, there is good chance that we will miss this physically to understand, though mathematically much more rigorous than this. If I start with say x cubed term, I will as well miss, okay, a lot of things. The solution itself I would miss. Okay. So it is important that it is complete up to this m is equal to 1. The next condition that I am going to put forward comes from my jumps. Next condition is that the discontinuity across elements, okay, or it should be at least continuous, let me put it like that. The interpolation function which I am going to choose should be continuous at least up to m minus 1, continuous at least up to, sorry, m minus 1. Is that clear? So in our case, what does this mean? This means that, what is m? M is equal to 1. So it is continuous up to m minus 1. So the first derivative need not be continuous. Okay. Usually it is it's a practice to put down continuity by means of a symbol, say c, and then put it like this, okay, m minus 1. So in other words, when I say that my continuity is now not there for the first differential, then the type of element that I am using is equal to, or is called as C0 element. Okay. So what we have been talking about now are C0 element which does not possess continuity of the first differential. Okay, they are C0 element. So since there are no continuity of the first differential, we landed up with that kind of jumps. Is that clear? So this depends upon, so you are theoretically correct, okay, to use this element as long as my phi p has the order up to m. Okay. So what is that we are using? We are using C0 continuity elements. Okay. If the slope happens to be continuous, which is the first differential, then what is the element I will be using? C1 elements. Okay. So when someone says I am using C0 elements, now you understand what it means. That is the second condition. I am just pointing out 4 important conditions that should be met by the interpolation function. The third condition becomes very important, is that when I define an element using an interpolation function, okay, and put this element in a mesh, okay, I define an element with a particular interpolation function and put it in a mesh, then and apply the boundary condition, apply a boundary condition such that I specify the differential up to m minus 1. For example, in this case, suppose I specify constant strains, okay, or constant displacement or constant strain, okay, then the element should be capable of taking, okay, that differential. In other words, when I say that I specify constant strain, the element should have the ability to respond to my boundary conditions by assuming a constant strain throughout. Okay, usually this is achieved even with a few number of elements for well behaved ones, but for some other elements you may have to keep increasing the numbers, but nevertheless the constant ability to take constant strain should be present in the element, okay, so that in the light of I reducing the size of the element, ultimately I will be able to get to a constant strain state. There are more advanced concepts like patch test, which is based on constant strain elements and so on, okay, but it is important at this stage to understand that constant strain state should be there. Okay. Now, what does it mean for us? Can I just think for a minute and tell me what does it mean for us, or from the point of view of writing down the interpolation function? Yes, that is correct. So, if I say u is equal to a0 plus a1x plus a2y and so on, it should at least have u is equal to a0 plus a1x plus a2y. So, that I will get a constant strain to be depicted or to be shown by this element. Is that clear? Okay. Fourthly, I should not introduce any geometric anisotropy inside the element. What do I mean by geometric anisotropy? Okay. Suppose I have an element which is like this, and I have another element like this, okay, where of course this is say x and y and x and y. What do I mean by geometric anisotropy? Just think for a minute, because it's a concept which comes very naturally. Just look at this and then tell me what do you understand by geometric anisotropy. It's very simple. What is anisotropy? They are different, correct. So, they are different. Okay. Isotropy means it is the same. So, they should not be geometric anisotropy. Correct. So, the properties of the element should not depend upon the type of type of coordinates. The property will depend upon the shape, okay, but it should not depend upon the coordinates, or in other words, what does it mean? Whatever be the type of coordinate system that I choose, whether I choose this coordinate system or this coordinate system, okay, I should have the element to behave in the same fashion. Is that clear? So, what does it mean from our interpolation function point of view? What does this give me? What does it mean? Is it clear that whether I have an element like this or like this, so it should behave in the same fashion? Yes. So, in other words, suppose I say u is equal to a0 plus a1x plus a2y plus a3xy plus and so on, okay, then, or in fact I should go further than a4 say x squared plus a5 y squared plus and so on, then if I introduce x squared, I should introduce y squared. So it should be symmetrical about say a center, right. That is brought about by writing down these expansions by means of or in a term called Pascal's triangle. Okay, Pascal's triangle. Now what I am going to do is to write down one term and give you 1 minute for you to fill up. Okay, let us see, just think about it. Okay, so Pascal's triangle I am going to write like this: 1 x y. Okay, now next is x squared x y y squared, right, that is the quadratic term. Then the next line, just think about it and write it about the center. So what will be the next term? X cubed, x squared y, x y squared and y cubed. So if I introduce next term as x in the line, if I introduce x squared y, I should introduce also x y squared. Okay, so that is another condition. So whenever I am in this line, for example, okay, I should have included what all are there above, and also about the center it should be symmetrical. We are going to talk a lot more about Pascal's triangle or some more about Pascal's triangle later in the course, but right now it is important that we understand, okay, that we cannot introduce this geometric anisotropy by including only, okay, terms which may bias my whole interpolation. Is that clear? Okay, any questions? Right, we have already written down the easiest way to write down interpolation, the easiest way to find out interpolation, okay, which we called our easiest way to go to shape function. What was the easiest way? Remember that we wrote down u is equal to say a0 plus a1x plus a2y plus a3xy, which means that I included up to that. Okay, for example, we did this for a rectangular element. Then what did we do? We then swapped a0, a1, a2, a3 for u1, u2, u3, u4 or v1, v2, v3, v4. In that process, okay, in that process we got what are called as shape functions. Is it clear? Okay. Now the question is, should I do that every time? Yes, you can do it every time and get the shape functions. Okay. Now, but the only thing is that it should fulfill all these conditions, whatever we have been talking about. But sometimes it becomes difficult to keep on inverting this A matrix. Okay, it becomes difficult to invert. If you can do it, well and good, go ahead, that is the most scientific way of doing it. But it may become sometimes cumbersome. So I would like to get a much easier way of doing things. Okay, one is by inspection. We are going to see how by inspection you can write down shape functions. The other is by using Lagrange interpolation, right. By the way, what are the properties of the shape function which you already know? Sigma n is equal to 1 and n I or n1 is equal to 1 at node 1 and 0 at other nodes and so on. Okay. So we are going to use Lagrange interpolation, okay, and we will use another type of interpolation later. Let's now right now stick on to Lagrange interpolation or Lagrangian interpolation, okay, which is I probably all of you are familiar with it. Is it clear? Okay. Now let us look at how to write that. How many of you remember Lagrange interpolation? All of you, yeah, very good. So why not you write it? Say for example, I write a field equation is equal to sigma I ni phi I. I deliberately have written like this because that phi can now be replaced by means of u, v and so on. Remember that. So I know that there is a lot of confusion, students get confused on looking at so many a to z, psi, eta, phi and all these things. I think you have to get used to it, Okay. So in other words, when I write like this, I also mean that the displacement u can be written as ni ui and so on. Okay. Now, what are these n's? And what does this Lagrange interpolation? Yeah. Question? Is clear? No. What I am trying to say is, we are trying to write down the interpolation function, okay, without going through my earlier route that u is equal to a0 plus a1x plus a2y and so on. Now, I am not going to go through that route. Okay, I am trying to get this interpolation. After all, I am interpolating the values. So, I am trying to get to this interpolation through another well-known technique like Lagrange interpolation. Is that clear? Now, in other words, what does Lagrange interpolation does? It passes a curve, okay, along the well-known or indicated points, okay, without bothering about the, what is that? What does it not bother? It passes through these points, but does not bother about the slope to be satisfied at these points. Okay. So, it would coincide with the actual curve, okay, at these points as far as the values of phi is concerned, but will not satisfy the gradient or slope of the curve at these points. So, in other words, if I now plot, say for example, this is the actual curve that I have, okay, the Lagrangian interpolation, suppose these are the points which I am taking, the Lagrangian interpolation will follow, okay, go like that. It will follow these points and it will satisfy the values at these points, but they will not make the slope of the curve that has been predicted or has been interpolated by the Lagrangian interpolation to be the same as that of the original curve. Is that clear? So, you can very clearly see that it passes through all these points, but the slopes are different. There is another type of interpolation which does this, where the slope continuity is also satisfied. Hermitian interpolation or Hermite interpolation, which we are going to use, okay, next case. But by the way, why am I interested right now in Lagrange interpolation? Hey, you link up what all I said till now to this.
We don't know the derivative.
No, it's not that we don't know the derivatives. C0, beautiful. So, we are interested in C0 elements. So, I am not interested to right now to look at, you know, continuity of the first derivative. For another problem, say for example, when I go to beam problems, okay, then I have to put continuity of the slope as well. So, I will give that as a one of the degrees of freedom. But right now, what is that I am looking at? I am looking at only a C0 type of element, okay, and hence, is it clear? Okay, and hence I am only looking at a Lagrange interpolation. Now, how do I now write down Lagrange interpolation? Do you remember how you write down? Say n1 is equal to what? x2 minus, correct, that is it. So, x2 minus x into say x3 minus x and so on, divided by say x2 minus x1 into x3 minus x1 and so on. Is that clear? Okay, that is n1. So, n2 is what? x1 minus x into x3 minus x and so on, divided by, in this case, instead of x1 it will become x2. So, x1 minus x2 and so on. Is that clear? x1, yeah, right, x3 minus x2 and so on. Now, I am going to talk about a much more difficult concept later in the course, but right now, okay, let us see how we can write down an interpolation function for a rectangle. Okay. Now, this is simple, this is one dimensions you can write down. Suppose now I am going to talk about a rectangle. How do you combine? I am going to give you 2 minutes to just think about it, okay, and see whether it is possible for you to combine the x and the y direction. The rectangle looks something like this. So let us say that that's 2b, that's 2a, and that's x and y. 1, 2, 3, and 4. Those are the nodes. Just take 2 minutes to realize what is it, because this is so, though it is not a very practical element, but there are a few concepts that you are going to get out of it. Just look at this and see how we can use Lagrange interpolation to write down. Okay, I will give you a clue. First take the side 1, 4, okay, that is this side 1, 4. Write down, okay, write down a linear interpolation, okay, in that side, same way 2, 3. Then do another linear interpolation from left hand side to the right hand side, or in other words, we go to a bilinear interpolation, okay, linear in the x as well as y direction. Is that clear? Okay, let's just look at this, and let me give you 2 minutes to do that. I'll slowly give you clue one by one so that you will understand what we are trying to do. So in other words, the first step that I want you to do is to write down what is n1 and what is n4. Once I have n1 and n4, any field variable phi, okay, can be interpolated between 1 and 4 along y. Is that clear? Is that clear? Same way 2, 3. Once I do that, let me call the interpolation along 1, 4 to be, say, phi 1, 4. Okay, along 2, 3 to be phi 2, 3. What does this remind you, people who have taken CAD course? Bilinear, okay, interpolation, which you would have used probably in patch, right? Parametric patch, bilinear patch as you would have called. So phi 1, 4, and write down phi 2, 3. Then interpolate between phi 1, 4 and phi 2, 3. Okay? Is that clear? Okay. Now, what is n1? Pardon? No, I want it in terms of b and a, b, b minus y divided by 2b. Okay. Oh, okay, fine. This is 2b and I have given this as 2a, and yeah, fine. Let me stick to my this thing. So let's say that 2a and 2b, so that I'll be consistent later. Y minus b divided by 2b. Okay, this comes out straight away from substituting, mere substitution in the Lagrange interpolation. Right? n1. This is y plus b divided by 2b. Okay, so 2a, and this is 2a and 2b, so y minus b by 2b, and that is y minus a, y plus b divided by 2b. Sorry, b minus y, sorry, yeah, because minus y and b minus y by 2b, correct, b minus y by 2b and y plus b by 2b. Right? So what did I do? y4 minus y, actually it's very simple, y4 minus y divided by y4 minus y1. y4 minus y1 in this case is 2b, okay. y4 happens to be b, so b minus y divided by 2b, that's all, nothing else to it. In the other case what happens, it's just the other way, okay. Both of them become minus, and hence minus in the numerator denominator cancel, so you get y plus b divided by 2b. So you can now write down phi 1 4. What is that you are doing? You are linearly interpolating in the 1 4 direction, right. Do the same thing for 2 and 3 also, you can do it, right. Now interpolate in the x direction, interpolate in the x direction. How do I do that? How do I do that? Just look at that, just 2 minutes. You just see it, you will be able to understand how to do it. Is this clear? Till now it's clear that you are interpolating linearly in the y direction. Is it clear? Okay. First thing, you have finished that. Then I want you to linearly interpolate in the x direction. So in other words, what I want to say is that I can write down phi as a minus x by 2a, okay, by 2a into phi 1 4 plus a plus x by 2a into phi 2 3, that's all, right. So it is something like linearly interpolating it here and then again this. Is that clear? Okay. So there will be lines which will go from, linear lines which will go from this end to that end. Is it clear? Linear lines which will go from this end to that end. So ultimately what is that you are going to do? Phi 1 4 you are going to substitute, phi 2 3 you are going to substitute and get n. So the first concept that comes out is that for this rectangular element we have used bilinear, okay, interpolation, linear in both cases, which means that it is equivalent to using up to xy, right. Okay. Now so ultimately what is that I want you to do? I want you to write down phi in terms of n1 phi 1 plus n2 phi 2 plus n3 phi 3 plus n4 phi 4, okay. So this is for local n1 n2 only in that direction, okay. Now is it clear? Any questions? Okay, is it clear? Everyone comfortable with it, right? So it is just interpolation by Lagrange method. So what is that you get ultimately? I have not yet got your answers for n1 n2. So what is n1? Yes, a minus x into b minus y divided by 4ab. Now how do I check whether this answer is right? First check, straight away check. How do I check this? Yes, very good. So substitute for node 1 x and y values, okay. You substitute this node 1 x and y values, and if what should you get? n1 should be equal to 1, okay. See whether you are getting 1. So what is this? Minus a comma minus b, substitute it, you are getting 1, okay. That is the first check. What is the other check that you can do at this stage for the shape function? It should become 0 at all other positions, at all other nodes, rather not positions, all other nodes it should become 0. Does it become 0? Yeah, straight away it becomes 0, right. Okay. Now what is n2? No, a plus x into b minus y, correct. A plus x into, that's why I am telling you these clues. Just check before you answer whether you are right on target. So what is n3? A plus x into b plus y divided by 4ab, okay. And n4 is what? just the other way, a minus x into b plus y divided by 4ab. So that becomes a minus x into b plus y divided by 4ab. What is the other check that you can do now? Add them, sigma of n's should be equal to 1 and so on. Now, okay, this itself I am not, yeah, it's a nice way, it's a much better way than doing, what is that we did? We interpolate Lagrange interpolation x and y directions I did and so on. I'm happy because this you now know that it's much easier than writing down in terms of A's, because it works faster than this, than what we did in the previous case. But I'm still not very say happy when I want to work out. I feel that I can get a much easier method. Can someone suggest, look at this, and can someone suggest a much easier method to do it? Now, what do I mean by that? Can you use these properties of n's? Can you use the properties of n's to write down the same thing by a much easier method? I'll give you, do you understand? Now, the properties of n's are well established. By inspection, can I write down? What people call, finite element people call as by inspection, can I write down? One second. Let me give you clues. Okay, there are a lot of ways. Area we don't usually use for this, we use it for triangles. Okay, let's not worry about that right now. But I'll give you a clue. Do you understand? In other words, I can write down the same thing by inspection. Okay, by inspection, looking at certain properties of n's. Right? In order to do that, okay, let me say that I can write down this line to be some equations to these lines. So what is that? For 1, 2, y is equal to minus b. Okay, and similarly you can write down for 2, 3, x is equal to a, and so on. Okay, that's your clue. I'll give you 1 minute, think about it. Now, what is that I'm going to do? I want, number one, I'm going to use one property which I said that this shape functions should be 0 at all other nodes except to the node to which it is wedded, or ni should be equal to 0 when I not equal to j, and should be equal to 1 at the node I. That's the clue. Okay, now think about it. In other words, okay, let me give next clue. I can write down straight away, but I think it's nice that you think. In other words, I should have terms here in such a fashion that all the other 3 nodes shape functions at those fellows should disappear. Okay, that's the next clue. Is it clear? Okay, the third clue I'm giving is that this node does not lie in these 2 lines. That node doesn't lie in these 2 lines, and all other nodes lie in these 2 lines. Okay, these 2 lines. What's this line? Y is equal to b. Y is equal to b, x is equal to a. So if my equation involves these 2 lines, then obviously all other guys would go to 0, period. Right? Is that clear? So I can write n1 to be, is it clear? n1 to be some c1 into, what is this equation? X minus a into y minus b. That's it. By inspection, I can use these properties of n to write it. Okay? Though please don't forget the basis that we came from linear interpolation, that we introduced x, y, and so on and so forth. All these things are there, but it is much easier to write it down by inspection, because every time I don't want to do all these things. Okay, it's easier to remember it looking at it like this. So I can say that n1 is equal to say c1 into a minus x into b minus y is equal to n1, the same n1. So now how do I now get this fellow c1 period, that's it, very good. So I'm very happy that n1 is equal to 1 at this x is equal to minus a and y is equal to minus b. So you get obviously c1 to be equal to 1 by 4ab. So you can very easily write down this equation. Is it clear? Okay, so I'm going to write down in future by inspection only. Okay, I'm going to just look at the properties and I'm going to write down these things in future by inspection, right? Okay. Now I'm going to give you a small problem, a very simple problem, just a modification of this. Let me see whether you are able to write down the shape functions. Just a small modification, nothing great. In fact, you can substitute it, but I don't want you to substitute in this, but I would like you to write it by inspection. Is that clear? I want you to write down this by inspection. Let's take the same element. Okay, psi, say I'm going to put psi eta coordinates. Okay, it should be more square, and this varies from -1 to +1. Okay, -1 to +1. Right, psi eta coordinates -1 to +1. Write down n1, n2, n3 by inspection method, not by substitution of whatever, you can substitute 2a, 2b, but I would like you to write it by inspection method. What is the first thing you do? You write down the equation of all the lines that exist. Okay, now what is this line? Eta is equal to -1 and so on. Yeah? Yeah, what is that you get? n1, what is n1? Very simple, straightforward, but you just do it with this. 1 minus psi, is it eta minus 1 or 1 minus eta? 1 minus eta, okay, 1 minus eta by 4, that's it. Okay, 1 minus psi into 1 minus eta by 4. So you can now write it down by inspection. I mean, I'll teach you as we go for higher order elements how to do that, but right now the concept is quite clear. Okay, I am making use of these facilities or this property of n's. Is that clear? Okay. Now I have a problem. Always we come up, see how do we proceed here? We come across a problem, we try to solve it by going to the next step of theory and so on. The first thing I know, in fact even before I started this class, 1 or 2 people asked us, sir, if you look at the type of elements we have used yesterday also, the last class also, when we looked at the elements, they were not necessarily so nice elements. They were not rectangular elements. Okay, they are quadrilateral elements. Okay, and how do you now handle that kind of elements? That's number one. In other words, all of us are worried about what we call as that integral. Okay, that I know a lot of people right in the first class said, oh God, we have to integrate it, triple integral and so on. Right? I know that it's not going to be easy. It is not that you and I face, everyone faces problems of integrating. Okay, it's not going to be very easy. That's number one. So how do you handle shapes which are different from simple shapes of elements like this? I can't, obviously, when I go to very complicated geometry, I won't be able to fill up that geometry with such nice shapes. Okay, when I have automatic mesh generation, I have no control over exactly the shape of the elements. Number 2, you have been interpolating only the field variables. You have been interpolating phi, or in other words u, v and so on, but you have not interpolated, say, the shape. Only if I am able to, or in other words, as far as it's rectangle it's fine, but how are you going to introduce that shape also into the element definition? Okay. So, shape also we will interpolate it. What do I mean by shape interpolation? Is it possible to say that x can be interpolated by means of the x's or x1, x2, x3, x4 of the 4 nodes? In other words, we now move into a realm called isoparametric elements. Okay? So, we are now into what are called as isoparametric elements. Isoparametric element is a concept, okay, which is applicable to a number of elements. Essentially, we have to understand, to appreciate isoparametric elements, the concept of natural coordinate system. You have to appreciate the concept of natural coordinate system. But isoparametric element is a concept which is applicable to brick element, or in other words solid elements. It is applicable to plane elements, it is applicable to shell and so on, okay, shell and maybe plate. So, isoparametric elements is a concept, is generic concept, right. So, we will study isoparametric element, and why does this become important? It is the most important element or the most important concept that has evolved in finite element analysis. The central, I would say, crux or the development of finite element analysis over the years has been possible because of this beautiful concept called isoparametric concept. Okay. So, the whole development has depended on this, and the whole advantage of finite element analysis is because of the ability to handle, okay, odd shaped elements. The whole thing was possible by isoparametric concept, and it is the most important element that is used in commercial packages. Whatever element you have been handling or you have been seeing, the results of which you have seen in the past few days, have been possible because of this concept of isoparametric elements. Hence, it is important that we understand the isoparametric elements. The concept is, I know that it's a difficult concept to catch, so I'll explain that slowly in the next class, but right now it's important to understand that the whole concept depends upon what are called as natural coordinate system. It depends upon the natural coordinate system. So, the first thing that we are going to do is to look at natural coordinate system, what we mean by natural coordinate system, and then we will convert all these things in terms of natural coordinate system. That gives us a big leeway as far as the coding, computer coding is concerned. In other words, isoparametric element not only makes it possible to do practical problems, but also gives a method of coding, okay, so that your software development itself becomes very systematic, and it's possible to evolve a very nice software. So, we will talk about the isoparametric concept in the next class.